we're saying for this. So when we talk about forces in general, we're talking about a push or a pull. A push or a pull. And there's another definition of forces. Can I just hold that? And the other definition of forces involves what we're about to actually derive. So I don't want to give that definition just yet. I think this is going to be Alan. Oh, they're both Alans. I don't want to give away that other definition of force yet because it's going to probably give away what we're doing, what the point of this lab is. What you're also going to do, and I'm showing you guys this stuff now because we're going to use it in the lab. This is a knob to push the entire thing with, so that when you actually use the push sensor, which is right here, there's a little spring scale inside of here that measures tiny deviations electrically, and then it converts that into an algorithm to give you the amount of force you're applying. So when you push on here, it measures the push or the pull. You can also attach a little hook. This little hook right here allows us to pull on things and measure the force pulled. We're going to be pushing, so I have it set up this way, and I'm simply going to push this across the track like that. I have it on the low Newton sensor now, under 10 newtons, because I know already from this experiment, having done it myself, that it's going to be less than 10 newton force, and it's more precise by using a fine-tuned scale. I also have chosen, again, the low G accelerometer instead of the high G accelerometer, because I know that the acceleration will also be very low. So I'm going to start with 100 grams of mass. The accelerometer has an arrow on it. The arrow on it simply tells you the direction you want to face it. So I'm going to go ahead and do that. Now, it doesn't matter whether it's forward or backward as long as the arrow is parallel to the direction of motion. So I'm going to use this high-tech situation, keep this down, which is me just putting this, there we go. So I'm putting the weight on the actual wire to keep it in place. So it's not going to move right now, and the weight's right next to it. All I'm going to do is push on this, but our goal is going to be to measure the value. So what I need to show you right now is what we're actually reading. So let's see how far this can stretch. Very far along. Sec. Low. We're going to connect these two. Let's see a little bit better. How far am I going to move this? Let's see. Here. As far as like here, probably. Get this to connect. I can. All right, this works. Didn't know if that was going to actually work or not. What number is this guy? Doesn't say, of course. So what I'm doing right now is I'm turning the sensor from being a Wi-Fi configured sensor into one that connects primarily with the USB device. So give me 1 sec to do that. Okay, enable over USB is on. Should be appearing on the left side. Okay, so we have our data port here set up, and what we're going to do is we're going to collect data for this apparatus. Take a look at what it's reading already, though. It's reading that there's currently a force and acceleration. Is it actually moving? No, right? Okay. So it's just not calibrated. So the first thing that I'm going to do is I'm going to go up to sensors. I'm going to choose 0, and I'm going to zero out both sensors by hitting all sensors. Now, the data we're going to collect from this experiment is really going to be just a general idea of what's happening that we're looking for. We're not really concerned with the actual numbers right now, but really what's happening, what the trend is. So the trend may be like, is the force going up as acceleration goes up? Is one going up as the other goes down? Is one double the other value? So we're going to try to come up with a relationship that exists amongst these. Now, if you took physics or physical science or like some course like that earlier, you probably know already what you're going to expect. You don't have to say it, but you know what you're going to expect. But let's prove that numerically here with this device and this setup. Jack?
Is this measuring the force and acceleration horizontally, or is it doing?
Yes, only horizontally. So this accelerometer, because the way I set it up, is only measuring left to right. If I rotated it, it would measure up and down. The force sensor, because I'm pushing left to right, it's only a horizontal force I'm applying. But if I apply it downward, then it would be an applied force downwards. So again, a force is a push or a pull. Push or a pull. Think about your weight as a force. the weight with which your body pulls you down to the earth is actually a force. So you notice the number is changing as I move the cart, right? We're noticing the acceleration. So we're going to see numbers like that, and we'll see the acceleration going this way is fluctuating. But we want to collect data for this for a couple seconds. Can you hold that still, Jack? And I'm going to make it, instead of 2 seconds, I'm going to make it like 5 seconds instead. Okay. Can you do me a favor and hit play on this corner down here? I'm going to try to do this with a nice constant motion. All right, when you're ready, hit play. Go ahead.
Okay.
Okay, store that real quick. Did it take? Okay, nice. Yeah. So store that real quick in the file cabinet.
Wait, I can't even see the screen.
Oh, it's sorry. It's this guy right up here. I got it.
Okay.
All right, give me 1 second. 1 second. Okay, ready, set, got it.
Wait, it didn't start. Sorry. Sorry. Ready, set, go.
One more time. So store that if you can in the file cabinet.
Ready, set, go.
Does anybody see what's happening there? The keyboard got caught on the desk, so this is going to have some negative force acting. That's all right. Store it stuff. Let's do one more.
Ready, set, go.
Okay. Thank you. So, again, the point of this is not going to be to analyze data, but to look at trends. And the reason I say this is because I already looked at this, and I recognized that although the data is nice, it doesn't give us the precision that we're really actually looking for here. So let's take a look at the last run that we did, which was run 4. Okay, all right. So here's what we're noticing, and I know this seems crazy. I'm going to first change my acceleration scale. Do you see this big spike up here? Where did that spike up come in? When I did what? It's when I stopped it. Okay? So the acceleration this way was considered negative, direction this way was considered positive. I knew that when you push with the force sensor, it's always considered a negative force. So I made sure that when I put the arrow on there, that the acceleration it's measuring is going to be considered negative. Then, because I pushed back that way against it, that was a positive acceleration I was applying to the block to make it stop, or the cart. So what I'm going to do is I'm going to change my y values here. I'm going to go to my graph options, and I'm going to change my y-axis here, but I want to change that for the second parameter here, so the second one down here. I'm going to change the top axis to like 0.5. Okay, let's take a look at what it looks like. Yeah, that looks much better. Now, here's all I want you to notice. All I want you to look at, and actually I can do with time also, 0 to 2 seconds. Let me change that as well so you can actually see what I'm saying. So then the time scale, let's go from 0 to only 2 seconds here. So I'm changing my window settings right now. Right on your TI-83, you have the window settings. That's all I'm doing right now. And look how nice that is. And I know you're like, how's that nice? What does that even mean? How's that nice, right? But what's nice is this. We notice that while there's a negative force, we have negative acceleration. What we also notice is that where the force starts to get less, the acceleration was also less. Where the force becomes 0, the acceleration is suddenly 0. So although the data itself, and I did this, I took all these tables, used Excel to calculate the ratio of them, it wasn't consistent enough to prove mathematically that it would be a worthwhile experiment. We're going to do a couple others that are really good, that the data is actually perfect for. But what I want you to just see is that spike in the force, spike in the acceleration. Almost no force, meaning less force, closer to 0. That's the 0 force line right there. Close to 0 force, acceleration is pretty much close to 0 there. Graph goes up, graph goes up. Graph goes down, graph goes down. Up, up, down, down. Do you see what I'm getting at here? So every single spike along the force graph also has a spike along the acceleration graph. So with that information and your knowledge of Algebra 1 and 2, I guess, but really only Algebra 1 you need for this, what conclusion can you draw? What conclusion can you draw based on simply this concept of every spike is a spike, every trough is a trough? What do you think, Christina?
The relationship between force and acceleration are directly proportional with each other?
Yeah, they're directly related to each other. Very good. They're directly related to one another. And that's part of what today's lesson is going to be about. So we're going to utilize that when we get to what's called Newton's second law. Now, keep in mind that this setup we just used, the assumption was that there was no friction at all because the cart was rolling smoothly, and that the only overall force acting is the force of that push that I gave it, and that's where this data actually comes from. Jack?
On the graph, when the line goes into the positive value
Uh-huh.
of the acceleration and force, what's happening at that moment?
I took the force sensor off, and it's just not calibrated properly. So it should be at pretty much 0 at this point. There should be no force afterward,
Oh.
and the acceleration would be 0 for a while. Then when I stopped it, the acceleration spiked up there. This should pretty much be 0, and it is close enough. Again, for all of these devices, you're going to get stuff that's close to 0, but if I continued on, see what this does actually run around 0?
Yeah.
So that's when I removed the force at this location. Yeah, that's a great question. This is really important because you know what? Right now in AP Physics, we do so many labs. We do enough labs in here, but I think we do more like I give them, just as students, the apparatuses and say, make up your own lab that allows you to illustrate X, Y, or Z. Now, while doing that though, it's really important to recognize what part of your data collection matters. What did I just do? I went from 0 to 2 seconds. After 2 seconds, I stopped applying that force. So why do I care about the rest of the graph, right? When I stopped it, okay, you can see a huge spike in the acceleration. Why did I rescale this axis? Because now this graph has some meaning to it. A moment ago, it had no meaning. It literally looked like the graph was on the x-axis because we were so zoomed out. But the minute I zoomed in close enough, I saw the fine-tunedness of it. We're going to be doing exactly that with friction force in about a section or two. And the concept of friction is, hey, this might feel smooth to you right now, but it's not. There are little mountains all over the desk. And you know that from your biology course when you look at a microscope. When you look under a microscope at something, you can see. And I did this in college. The first engineering lab we had was called surface quality. And we looked at the surface quality of polished metal. What you would think would be like super smooth, right? Polished metal, which is what goes under glass to make a mirror. That's how you make a mirror, polished metal and glass. And that alone, polished metal, although it seemingly is very specular, is actually quite what's called diffuse. It's quite jagged, the ridges. So even materials that we say are pretty much frictionless have some sort of surface contours to them, meaning like little ridges and mountains and valleys. And that's what I'm talking about here. Even though it's not the same thing, this is analogous to the idea that when I zoomed in on the acceleration graph, I saw all these little spikes. But if I zoomed out up to where it should have been, up to like 4 is listed as here, we would see nothing. We would see what looks like a flat line, and then we saw that really, really, really big spike when I stopped it. So we really lost the meaning of the graph without zooming in. So part of today's demo, besides illustrating that we know that F and A are proportional to one another, is also discussing the concept of what data is actually valuable in a lab. So when you're doing lab reports this year, or when you're doing your lab reports for the next one, we're going to be looking at force of friction for kinetic friction actually. I want you to consider that certain portions of it matter and certain portions don't. So if I were a student and I were turning this in, and I were able to say screenshot this or have an image of this right here, I would make sure to use this image here, and maybe even stop here. And that would be the end of it, and this would be the end of it here, discussing that afterward there was no force applied, so there was really no acceleration. Okay? Again, just proof of one of Newton's laws that we're going to be looking into more and more. All right, disconnect. I'm going to go back.
You're gonna go to the bathroom.
Yeah, go for it. Yeah, go. I know.
Thank you.
Yep, you're good. Check.
Those things called the contours or something?
Surface contours. Yeah. All things on a microscopic level do have some sort of surface irregularity, or, you know what I mean?
Yeah.
Some sort of topography to them, if you want to use that word too, right?
And is there an example of something that's perfectly...
So there are some things that are really close to being frictionless, but there's no actual physical material that is frictionless. Because the concept of friction is resistance, and any contact creates resistance. But there are certain things like, have you ever moved furniture before?
Yes.
And you put these like either felt pads below and it's easy and it's smooth? And that's a good example. We're going to use felt actually. But there's a material that's called Teflon. Have you ever heard of Teflon? It's on like non-stick pans. That's why they tell you not to use metal on a non-stick, when you cook like eggs, you know, the pans that never have anything left behind. It's like, how does that work, right? It's Teflon coated, super low friction, so nothing sticks to it. But you don't want to ever use a metal spatula on that because you rip off the Teflon and you consume the Teflon, which is not healthy at all. Has anyone ever done, what is it called? Iceless ice skating? I know that sounds crazy, but iceless ice skating? Have you done it before?
I see like that's how the cruises have like
Yeah. It's a surface made out of this plastic Teflon, and it's actually this white plastic, and when you skate on it, you create these little grooves, but what they do is every couple hours they go out and they spray it down with a coating of more Teflon and fills in all those little gaps. So it's constantly able to be used. You don't ever have to replace it. It doesn't have to be a certain temperature. What they're using there is Teflon as the material, and then this like spray that they spray with. I don't know about health-wise of how that works and all, but I'm not inhaling the spray, but just thinking about that, I wonder what that's like. But that's a very, very, very low friction surface, just like ice and metal together. Because ice and metal together, I mean, that's just ice skates, right? And we all know that ice skates have very, very low friction. I mean, do we know that or not? Is that clear? We've seen. Has anyone ice skated before in the room? Have a couple of you ice skated? Okay. If you ever have a chance, they have them in Rockefeller Center, and then like I think Central Park has one too. You should try it out, even if you haven't had a chance to ever. It's a lot of fun. Ice skating's a ton of fun, and it kind of makes me think of skiing also. Skiing, if people have skied before, very low friction skiing. So we didn't really have. What we didn't have time for just now, which I would have done with a little bit more time most likely, and we're going to do it in the lab, is vary the mass. Okay? I didn't have time to vary the mass, but what do you think would have happened? Think about this question. What do you think would have happened to the amount of force needed to push the cart if I had put more mass in the cart? What's logical? What's logical? I'm not even asking you, any sort of numerical values here, but what's logical? If I suddenly put more mass in the cart, what would have happened to the force that I measured on the screen there? What are you thinking? What are you thinking, Janice? What do you think?
We would have needed more force to push it.
You would have probably needed more force to push it. Okay, and yeah, you definitely would have needed more force to push it. And the rationale behind that is that what? What is mass really? Anybody know? This is a weird question. This is not something you learn in like younger science classes usually. What is mass really? Again?
Isn't it force divided by something?
That works, but yeah, that works. We're going to get to that definition in a little bit. And so she's saying if you have more force, and you want to get mass, you need more mass. Or if you have more mass, you need more force. But I'm asking something else. Like, theoretically, what is mass? And the answer is not, it is the amount of matter that makes up an object. Like, that's the classic answer. How much matter, how much substance you have. It's not the answer I'm going for right now, though. What's the other meaning of mass? You got it?
Well, weight varies on the force applied on you, the gravity, but mass is consistent with gravity.
Still not answering the question. I know what you're saying, Jack. We're going to get to weight and mass and how they're different.
Is the force on gravity on an object?
That's the weight of an object. That's what Jack was referring to. It's called the weight of an object. So this is a weird definition, and we're probably not going to get to it for a couple slides, but I'm going to say it now anyway because we've been talking. But mass is actually what's called the total amount of inertia. Inertia, yeah, I know. We're going to get to that phrase inertia in a little bit. Mass is really the total amount of inertia. Now, what is inertia? Here's what inertia is. Ready? This object right now, if I give it a little push, wants to keep rolling forever. It never wants to stop. Why does it stop, though? And it's unlevel, obviously, because the way it's like kind of catching. But why does it stop? It doesn't want to stop ever. It never wants to stop. But why is it stopping? What's happening? There are some frictional losses, whether it's air resistance or friction in the table. And I can do it this way, and we see it stops much quicker, doesn't it? But when I do it this way, it does not stop very quickly. So that takes a while. Or it has to hit something else to have an applied force. So when an object moves, it wants to move forever. It never wants to stop. It only stops because of some outside force acting on it. That's inertia. Inertia is the desire for an object to maintain its state of motion. If it's moving, it wants to stay moving. You guys know this, whether you realize it or not. Think about a hockey goalie. When a hockey goalie stops a puck, or when a soccer goalie takes a shot right to the stomach, right? And you ever see a soccer goalie save a ball that hits him here? The whole body gets kicked back, right? Because that ball wants to keep moving. But their body is applying a reactive force or an outside force to get it to stop. So an object in motion wants to stay in motion. While an object at rest, look at it. It doesn't want to move, it's at rest. It's really comfortable right now. When you're in a chair, that's what inertia is. When you're like, oh, I'm so comfortable, I don't want to get up. You're like in a recliner or like in a sofa. You don't want to stand up to physically get up. That's inertia really there. Your desire to stay at rest. But any object, anything that has mass, has inertia, has a desire to maintain its state of motion. If that motion is moving, it'll maintain motion. moving. If that motion is not moving, it will maintain a lack of motion, meaning not moving. Okay? Now, we talked about force already, but as a general definition, we call it the cause of acceleration. And the reason I do that demo first is because I want you to see that force and acceleration, as we saw, as Christina told us, force and acceleration are directly related. A force causes acceleration. Again, a force causes acceleration. And you might be saying, Mr. Howell, you're crazy. Because look, I apply force here, and this object isn't accelerating much. But just the fact that it's even moving means it must have accelerated. Because what's the current velocity, everybody? And if it's moving, it has a non-zero velocity, right? How do you go from zero to velocity to a non-zero velocity? You must have accelerated it. So even the littlest force accelerates it. The littlest force causes acceleration. And that's assuming that friction isn't pushing back, right? Because if I do the same thing, look, any acceleration, anybody? No, right? The desk isn't moving at all. But the reason it's not, the wheels are locked and there's friction in the wheels that are preventing the motion. So when I push, friction pushes back. I push harder, it pushes back. I keep pushing, eventually I can overcome friction. So friction turns out that force can vary based on how much I push with. If I push harder, friction pushes harder. I'm trying to give you guys like an overview of this kind of lesson because you're all here and there's a lot of people missing, so I want you to get like the nice information. They'll have to catch up on the video if they're not here today.
At the equilibrium, when there's an equal amount of force to the object, what happens? Does it actually get pushed or is it still stationary?
Then it's stationary. That's this. Ready? I push with 1 Newton. The desk pushes back with friction of 1 Newton. I push with 2 Newtons. 2 Newtons pushing back. 3 Newtons, though, maybe it exceeds the friction and then it moves. So whenever the forces are balanced, there's no motion.
So once the force is greater than the force pushing back,
It'll start to move. This is for stationary objects you're asking. If it were already moving, it's a whole other circumstance, and we'll get to that. We're not going to get ahead of ourselves right now.
Also, I just thought of a maglev train earlier.
That is one of the lowest friction existences, but there's still air resistance. But yes, he's talking about maglev trains, the ones that are levitating. Very, very low friction because it's magnetism, that force that's causing it to stop or move. But there is air resistance still, even though that's very low. You can look at what are called superconductive materials that move around these tracks that are levitating. I could even send you a video if you want to see this. But that's also really low. They're really, really, really cold materials. Christina?
How much force would you like 1 Newton?
Okay, that's a great question. So Christina asks, how much force is 1 Newton? And this is really important that we understand what a Newton really is. Now, my definition I'm going to give you is not going to be helpful, but let's talk about why that is. Here's what a Newton is, based on its units. It is the force necessary to move a kilogram at 1 meter per second squared. That's really what it is. You guys see that dash right there? That dash with units does not mean minus, it means multiplication. With units, for some reason, and you'll see this in all old textbooks and any textbooks really, this unit is really kilogram times meter per second squared. And kilogram is really what we're going to use to measure masses. And meter per second squared is acceleration. So a Newton is really mass times acceleration is what it physically is. But Christina's question, to go back, is really like, what is 1 Newton? So here's what I'd like you to do. Somebody just go to Google real quick and let's convert a Newton to a pound. So we get an idea of how much force we can think about. So just convert 1 Newton to 1 lb. 1 Newton to 1 lb. What do we get for that, Maura?
For 1 pound?
For 1 Newton. What's 1 Newton? So we have an idea of a conversion of what a Newton physically is.
0.225.
So, here to give you an idea. If you held a 5-pound weight, right, a 5-pound weight will be what? About, how many times this? 20 times this amount? So about 20 newtons is about 5 pounds. Yeah, it's obviously not going to be exact. So it's about that though. I want you to get an idea of a number sense, right? This can go into 1 about 5 times. So in my mind, I might start thinking about like, ooh, it's probably around 5 newtons is 1 pound force of push. Or sorry, yeah, 5 newtons is 1 pound force of push. So if I'm lifting a 1 pound weight in the gym, heavy 1 pound weights, those things are massive, right? They're like this big, they're tiny. So I'm lifting a 1 pound weight, I'm really lifting around 5 newtons of force each time I push up on that weight. Okay? So get an idea of a number sense. That's a great question. You should continue to do what Christina said. for all lessons going forward. If there's a number that you don't know what the value means, you should start to try to think about like a conversion factor. Okay, conversion factor. All right, let's see. Okay, let's keep going. So this is the definition of a force, a push or a pull, but it really is a cause of acceleration. We have two types of forces that we're going to focus on. Primarily in this chapter, we're going to focus on contact forces, things that are in contact. One of the few times that we use the definition in the name of the word, because a contact force is a made-up term. A force is the general word. We're specifying things that are in contact. So, for example, a push or a pull or friction, those are all contact forces. I tie a rope to something and I pull on it. That's called tension in the rope. There's tension. What's an example of a force that is not a contact force or a field force? A field force. You might have heard this if you're into Star Wars. Use the force, Luke. Use the force. Any Star Wars fans? Nobody? Well, anyway, yes, a force is pushing something at a distance, right? That's what Luke is using or the Skywalkers are using. But what would a field force example be? What would an example of a field force be? What do you think, Eduardo?
If you're like rolling a soccer ball and like it's because it can't roll forever, eventually it stops.
But why does it stop?
Because of friction.
So it's in contact with the ground. Good idea, though. I like the idea. Justin? Magnets. The minute you bring a magnet near something, it starts to move it. As a kid, isn't that the most amazing thing? It really is. It blew my mind. I still remember 4th grade being in, we had like these programs for science kids who were good at science. We had a program, we would go away from school for a day and do all these science experiments. And I remember like the first time looking at like iron filings and moving a magnet under a table and watching them physically move with it. And my mind was blown because I was like, I'm not touching that. How is that happening? That's a field force, magnetism. What's another?
Like planets orbiting, like gravity.
Gravity. The force is gravity. Planets orbiting, gravity is another field force. There's another one that we could think of.
No.
Yes, you can go to the bathroom.
Electric field.
The electric force, yes. Those are the main 3 field forces that we're going to talk about this year. We're probably going to just touch upon electric fields and magnetic fields just as a function of time in the course. Really interesting stuff still, not stuff that you want to ignore. Very interesting. But that's what field forces are. We will look at gravity as a field force for sure. Anybody know what the schedule is for
Yeah,
today?
36.
36? Okay. All right. So let's take a look at Newton's first law.
So why did Newton create all the laws?
So the laws are named after Newton because he was the first one to categorize and classify all these ideas. It does not mean the ideas weren't around before Newton. There were many, many civilizations around way before Newton's time, and Archimedes and Euler and Leibniz, all the famous scientists and mathematicians of like the 1,000 year to 2,000 year era. I guess that's the second. Well, what century is that? What millennium would that be? Is that considered the second millennium, right? Because the first millennium is 0 to 1,000. So in the second millennium is when most of the scientists that we know today lived, that we work a lot of our numbers and our theories off of. But prior to that, there were civilizations that understood this concept for sure. Like there's no way that Egyptians built these pyramids, or people, Romans I guess, and Egyptians built pyramids, if they didn't have these concepts down pat. So whether they were established or not as a law, it was still known by scientists and the scientific community. But Newton was one of the first to really term this. And just so you're aware, a lot of things that are named after famous scientists don't always come from them. And that's true even to today. If you do research, like when I was in grad school in engineering, I did a ton of research. I worked in a lab and I was a TA assistant also. And all the work I did, the credit, where did it go? It didn't go to me. It went to the teacher I worked under. So even if you're like a research assistant at a university, all the work you do, the credit for that usually goes to the professor that's in charge of everything. Because they're the one running the show, but they'll usually give credit where it's deserved to the students. Newton honestly was not giving credit to anybody. Newton thought of a lot of his ideas, but a lot of his students helped a lot of Newton's work, actually, a ton of Newton's work. And a lot of stuff is named after him that he actually didn't come up with himself. He validated, he discussed it, he verified it all, but not everything that he is named after actually is something he came up with. But that's the same that goes with a lot of stuff, just so you're aware. It's not just physics, biology, chemistry as well. So Newton's first law. This is inertia. Write it down in big letters. I-N-E-R-T-I-A. Inertia. Newton's first law is simply inertia. Inertia is the desire for an object to maintain its state of motion. To maintain its state of motion. Unless acted upon by an outside force. Okay, by an outside force. So right now, there is no outside force acting on my iPad. Sure, you're going to be like, gravity's acting on it, Mr. Howell. It is, for sure. But there's something called a normal force that we're going to talk about soon where the table pushes back. So right now, it's in a state of balance, which we're going to soon call equilibrium. Okay, but generally speaking, it's at rest. It wants to stay at rest. I love this chapter. It's one of my favorite chapters. I think you're really going to enjoy it. One of the really big positives, for those of you that have been struggling in the last chapter to know which formula to use when, there's really one formula we're going to use in the entire chapter. It's one, I know, it's crazy, right? One governing formula. That's it. And that governing formula, actually, oh, I'm almost there. I thought I was going to be timing it perfectly. It's like a slide away. That governing formula is Newton's second law, actually. That's what Newton's second law is. So we're going to get there in a second. So there's a term called net force. Net force. And what net force is it's an overall force. For example, let's say that, this is a great one. Let's say, let's just use quarters.
You can say the Jets right now are in a state of inertia.
The Jets are in a
State of inertia.
The Jets won the last three. Oh, and they're going to continue to
Going
win.
up, they're going to continue
Okay.
going up.
I'm gonna raise it back.
So,
Don't worry, I'm a Jets fan.
all right, I was going to say, get out of the roof. Me and Valentina are pulling on this cord right now. If Valentina pulls harder than I do, what happens? What happens if she pulls harder? Listen, please, listen. Christina, one more time. Listen.
Force moves in her direction.
Yeah. The overall force, the net force, is her force. So let's say Valentina is pulling with 500 newtons, and I'm pulling back with 400 newtons. Mine might be considered negative 400 because I'm going in the opposite direction. We're going to start talking about that soon. But the overall force, is simply called a net force. Net force. So just write overall force. And forces are vectors. Forces are vectors, meaning their directions matter. So if I pull to the right, I call that a positive force. If I pull to the left, I call that a negative force. Again, to the right is a positive force, to the left is a negative force. Up is positive force, down is a negative force. We're going to maintain the same established directionals as we did with projectile motion. So I guess before we can get to Newton's second law, I thought I was right there. It's a couple slides still ahead. Okay, so let's look at this first example here. A crate is pulled to the right with a force of 82 newtons. It's pulled to the left with a force of 115 newtons. It's pushed upward with a force of 565, and yet gravity is only pulling down on it with a force of 236. So the question is, find the net force in each direction. So here's how we're going to write it. The net force in the x direction is equal to positive 82 plus negative 115. And I know, yes, plus and negative is just minus, and soon we're going to write that, but I want to emphasize that we are summing the forces together. What is the symbol for sum in math? To sum a bunch of them plus, but what is it? It's like a big E, right? Anybody know what the name of that big E is? Sigma. The sum of the forces in the x direction is what we're doing. These right here, write yourself a note, please. These two things are interchangeable. They mean the same thing. F net in the x direction, it takes a lot to write that, so I don't write all those letters. I usually write it this way. And this simply means, this symbol here means the sum of. The sum of all the forces in the x direction. One is positive, one is negative, but we are still summing them together. Is that clear what I'm saying? Now, the way I can also have you think about it is this. Everything to the right is a positive force. Everything to the left is a negative. So everything to the left we could think of as a subtraction, really. I want you to recognize, and you should know this now, that addition and subtraction are the same operation. Subtraction is defined as adding the opposite. So really, I could rewrite this as 82 newtons minus 115 newtons, and therefore my net force will absolutely be negative. And it is negative 33 newtons. Based on our numbers we looked at earlier, divide that by 5 roughly. We're going to recognize that multiply by 5 roughly. Wait, which one is it? No, divide by 5 roughly, and we'll get the amount of pounds that we're actually applying overall to this object. So it's around 6 pounds, I guess, of force. Is about what that is. So that's the x direction. How about the y direction? That's the x direction. I'm going to do the same thing. I'm going to write the same symbols to start. Exact same thing. What do I write for the y direction? Juliet, good.
565 and plus negative 2.
Very good. And now that we know, we think of plus and negative as subtraction. This is really just 565 minus 236, yielding 329. So what does this mean? This means that the object is generally being pushed to the left and upward. Think about this logically, please. God bless you. A negative in the x direction means it's pushed left overall. Sure, maybe you pushed it right, but somebody else pushed it back left with more force than you did to the right. You follow what I'm getting at here? Okay, same thing here. Maybe you were lifting the object up, but gravity was pulling down on it. So the net force you actually give it is this much, really. So we're looking at balancing, a lot of balancing that we're going to see happening. Jack?
Are we going to be doing like a triangle and like on that?
So about 20 seconds away from it, Jack. You read my mind. Look at that. He's so excited, see? I'd be excited too. Okay, let's do it. So what we're going to do now is this. Let's draw the object here. Jack. Literally, the next step in my notes. You're like reading ahead of it. I like it. Very good. So the force is going to be to the left of 33. And notice I'm not writing negative on the diagram now because my arrow is to the left. Okay, when I use arrows, I'm not going to put a negative there because then it insinuates like a double negative. If the arrow is to the left, that already means negative. And then the force in the y direction is acting upward. And that's a far greater force, right? I should actually draw that to be scale. To be to scale, it would be 10 times as long as the other vector. So we're looking at something like that, really. So which way is the overall force acting? Go from the beginning to the end. Start at the dot and go to where the arrow ends. It's clearly acting in the what direction? Give me a directional. I don't need an angle, just a directional. Northwest. Very good. Because think about it, ready? It's being pushed west and being pushed north. Okay, the last part of this would be to figure out the angle theta and the overall resultant. This is the overall force we're going to figure out right here, and that's the angle theta. So we're going to determine both of those the same way you do with velocity. Fx squared plus Fy squared equals f squared. You got the f value. And then to get theta, use tangent again. Because you have opposite is 329, adjacent is 33. I got to let you go only because there's mass, or else I would keep going. Okay, we got to go down for mass. So we're going to leave off here. Don't even do any more homework over the break. I'm not even going to post the homework yet because we didn't get through enough. So take the break to relax. What can you think about over break, though? Just to think about. Project. Definitely start thinking about, and forces. But definitely start thinking about the project. All right, guys.